Let me pull up sharing on my computer. Okay. So I believe all of the slides and the lecture notes are posted online. So hopefully you'll be able to follow along with everything that I have here. So let me start maybe just a few quick announcements about things, just the usual announcements. Friday's lecture is now on YouTube, so feel free to go here to this link to take a look at it. Office hours will be at the usual time, usual place, so after class at 11, then in the afternoon at 4. And then the next homework assignment is due this coming Friday, homework assignment number 8. I was a little bit slow in getting it posted, but it is posted now. So what I'll say today is that a lot of what we're going to go over this week, some of the different concepts are going to be fleshed out in this homework assignment. So I will be discussing the results in lecture over the next couple of lessons, but just to say that if you really wanted to know the details of why some of these statements are true, then I would certainly say please attempt to do homework set number 8. Right, so let's do a quick recap of where we were. So last time we were starting to get into this idea of being a non-singular, excuse me, abstract variety. So let's say that we have here an algebraically closed field. So everything I'm going to assume for the day works over a field F that is algebraically closed. And if you don't feel comfortable with that, just think complex numbers, right? Now let's say that we have a prime ideal sitting inside of our polynomial ring over n variables. And let's consider this subset I. So remember before, we defined this here as an affine variety, right? So as long as my I here is a prime ideal, then this non-empty closed subset is what we're calling an affine variety. And it's just going to be generated by these m polynomials, f1 through fm. So once we have this, then we can talk about the Jacobian as this m by n matrix, right? So this here will have m rows and n columns, right? Just by looking at the partial derivatives of our polynomials. So with this, the first thing that we observe is that we cannot have more equations than variables. So m has to be less than or equal to m. Again, m is going to be like the number of equations. N is the number of variables, so we better not have more equations than variables. And the rank of this matrix, we want to be as large as possible. So we'll say that our affine variety is non-singular if we can define a tangent at every point. That is, if the rank is m for every point here in our Zariski closed subset. Right, so what I want to do is remind you today, why did we say rank is equal to m? Why was that kind of the trick that we wanted? So say that we have a point on our variety x. Right, we'll write this here in terms of our coordinates, a1, a2 through an. And what we see now is that this Jacobian matrix defines matrix multiplication. So here we have a linear transformation from the collection of n-dimensional vectors to m-dimensional vectors by literally just multiplying by this matrix. So that means that here we have a kernel set of vectors that maps to 0, and that's what we're defining as the tangent space. So again, it'll look like the kernel of this linear transformation. Or if you will, here we have a set of linear equations. So here we have m linear equations and n unknowns. And this is what we're defining as the tangent space. So there is a second way in which we could look at this tangent space, which is by looking at this pairing. So remember what this pairing does is, it says take a point here in our tangent space. Remember that our tangent space is going to be some vector space. And then take a polynomial here. Let's call it f. And we're choosing a polynomial, so intuitively it's an MP, which means that if I were to plug in p, I would get back 0. Right, so f evaluated at p is 0. And now we're going to send that to the following number. So this here is just the dot product. Here I just take this vector here, which is the gradient, dot product with the vector here from the tangent space. And this here is a very nice pairing and allows us to say that the dimension here of the tangent space is the dimension of this weird thing here that we're going to call the cotangent space. And we're calling it cotangent because it's like the dual to the tangent space. I have here this pairing that allows me to say that these here kind of look like they're duals of each other. Right, so again, we have the tangent space, TP, and then we have this cotangent space, this M mod M squared. Now, let's put all of this together to see why this helps. And a lot of this was really based on original work by Oscar Zariski back in the 40s and 50s. So first we know, just by looking at this pairing, as well as the rank nullity theorem from linear algebra, that the rank is M if and only if the dimension here of the cotangent space is N minus M. Right, so again, that's just a direct consequence of the rank nullity theorem from linear algebra. So in the special case where I have one more variable than equations, so N equals M plus 1, then the following 5 statements are equivalent. And so what I want to focus on for the moment are the first 3 that says that it's non-singular if and only if this M mod M squared is one-dimensional, and then that happens if and only if something here is integrally closed. So today I'm going to come back and talk about this integral closed in quite a bit of detail. I haven't mentioned it yet because we haven't needed it, but I am going to come back and talk about this in a lot of detail today. Right, so again, these 5 statements here are all equivalent. So let's see if we can't just kind of figure out, if we step back a little bit, what's really happening here. So we have these 5 equivalent statements. Now I want to try to piece everything back together in terms of what we're doing. So we talked about being non-singular at a point, but what if we know that this is true for all points? Well, that's what it means to be a non-singular curve, right? That it's non-singular at a point for every point. So that should be equivalent to saying that here this dimension of M mod M squared is 1 for all maximal ideals, because remember that every maximal ideal corresponds to a point on the curve. Right, so now we just translated this whole thing of being non-singular to a statement here about the coordinate ring. Right, and we're going to come back and talk about this in a lot more detail today. And these here should be equivalent to being a Dedekind domain. I'm going to come back and talk about what a Dedekind domain is a little bit later because the definition is a little bit hard to write out to start with. But again, the whole point here is that X is a non-singular curve if and only if the dimension here of M mod M squared is 1 for all maximal ideals. So this is really what we want to focus on today, this equivalence here. Right, so let's try to use this to write down some definitions. So remember, kind of going back to the beginning, we're dealing with this non-empty Zariski closed subset X. So it just means the 0 locus for M polynomials. And also remember that we have here our coordinate ring O, right? So it'll be this quotient here in terms of this prime ideal. And what this proposition says is that our affine variety X is non-singular if and only if the coordinate ring is a Dedekind domain. So remember, I started everything a couple of weeks ago with this philosophy of growth indeed, that we can either look at the variety X or we can look at this ring O. So now we've translated the whole question of being non-singular into a statement about this ring here. But I want to emphasize here that this is if and only if. So X is non-singular if and only if the coordinate ring is a Dedekind domain. So we're going to come back and formally define Dedekind domain later, but if you want, you can just simply say it's a ring that satisfies, say, a property like this here. Right, we have to be a little bit careful what this means, but we'll come back and then we'll talk about this in more detail a little bit later. Okay. So let's perhaps see all of this at play and focus very specifically on an elliptic curve. Right, so let's just try to make everything very down to earth to see if we understand what's happening. So we have here a cubic curve in short Weierstrass form, and we know that this here is non-singular if and only if this discriminant is non-zero. Right, so that was just kind of making it very simple. Remember that the discriminant non-zero means that it's an elliptic curve. So let's try to play around with this here a little bit to see what does this mean. So how does this relate to the Jacobian that we talked about earlier? Well, if you give me any affine point, right, I can stay away from the point at infinity for the moment, but let's take a look at any affine point. We can define the Jacobian in terms of these partial derivatives. And even though I didn't write it here on the slide, you know that the partial derivatives all are going to be computed by that function that comes from homogenizing this one equation. So if I take the partial with respect to x, I get this. Take the partial with respect to y, I get this. And then I have another one if I take the partial with respect to x0. But I'm going to kind of ignore that for now because we don't really need it so much. So this always has rank 1 when the discriminant excuse me, does not equal to 0. So here's the reasoning. If it does not have rank 1, then that means I can simultaneously find a point where all 3 of these partials are equal to 0. And in that case, it turns out that the only point where this works is this point here. Right, so again, what we're saying here is that the only way in which I can make all 3 of these partial derivatives vanish is if the discriminant is equal to 0. And in that case, then this point P here is the unique singular point. So again, as long as the discriminant here does not equal to 0, I cannot make all 3 of these partials 0, which means that this here has to have rank 1. Right? Rank just means that it's not the 0 vector. Right, so this we played around with for a few weeks, so we know this first statement. Now what's happening here in terms of being a Dedekind domain? So what does this really mean? Well, according to this previous result, the non-singularity of this cubic curve is equivalent to this coordinate ring being a Dedekind domain. So here we have polynomial ring and 2 variables modulo this relation. Right, x and y are related in this way. So I want to say a little bit behind what does it mean for this coordinate ring to be a Dedekind domain. So let's see, what we want to do is focus on a point on the curve and then stare at the maximal ideal corresponding to that point. Right, so that'll eventually tell me what are all maximal ideals that are sitting inside of my coordinate ring. So here's a maximal ideal. It's generated by these two, x minus the x coordinate p, y minus the y coordinate of p. Right, that's the maximal ideal. And if I square the maximal ideal, then that will be the ideal generated now by these 3. So here what we're doing is we're taking the pairwise product of the generators. So I'm going to take the first generator squared, the product of the 2, and then the second generator squared. So again, this here is the first generator squared. This here is the product of the 2, and this here is the second generator squared. So again, the square of the maximal ideal is generated by these 3. And if you're kind of wondering where this comes from, think of like the Taylor series expansion. So MP kind of says something about the linear terms in the Taylor series expansion. MP squared says something about the quadratic terms in the Taylor series expansion. Right? So here I have my maximal ideal and its square. Now I'm going to make a substitution here. Because the Jacobian back up here has rank 1, that means I can find 2 numbers, CP and DP, where the sum here is equal to 1. Right, notice that here, just kind of taking a look at like this, -3 x squared minus a, that kind of corresponds to the first column here. And then this 2p corresponds to the second column here. So we just want to say that even if maybe 2yp is equal to 0, then of course the first one is not equal to 0, and if the first one is equal to 0, then 2yp is not equal to 0. So I can always find CP and DP to make this here equal to 1. So now we're going to make a substitution based on this. Simply put, when I see x, I'm going to replace this in terms of s and t. And when I see y, I'm going to replace this in terms of s and t. Right, so we're just going to make a substitution so we can kind of make a clever argument here to get an idea of why is this a Dedekind domain. Right, that's what we're trying to do. So if we make this substitution, then now we see that the maximal ideal, well, before it was generated by x minus xp, y minus yp. Now it's generated by s and t. Right, so again, we just made a nice, clever substitution to say that this thing here is generated by s and t. But yet, let's take a look here at the quotient. Well, you might think that the quotient is also generated by s and t, but we've done everything here to make this really clever identity. What I see is I've chosen s so that it actually lies inside of the square of the maximal ideal. Right, so again, this here is just an identity. You just kind of multiply things out. You just check that it works. So here, this s, right, the same s that we had back here, back up above, I can write this as a constant times x minus xp squared minus yp squared plus x minus xp cubed. But here you'll see that each of these three actually lies in the maximal ideal. So the sum of the three has to lie in the maximal ideal. So that means inside of the quotient here, m mod m squared, s is 0. So this actually means that m mod n squared is spanned by t alone. Right? So just to recap before I go any further, MP, that maximal ideal, is generated by two elements, s and t. But m mod m squared is not generated by two because actually s is 0. So it's only generated by one element. Right, but of course that's really what the proposition said, that here the dimension should be 1. So let me just kind of piece everything together. In particular, the dimension here is 1 for all maximal ideals in M spec of R containing this prime ideal. Right, so remember that my MP was this maximal ideal here, but this really was a maximal ideal of R. I have to be a little bit careful here. So it's the maximal ideal of my polynomial ring. So if I now use the lattice isomorphism theorem, I know what every maximal ideal of the coordinate ring looks like. Right? So again, R was the polynomial ring, but OE is the coordinate ring. So now I have to take a look at the quotient by this prime ideal. Well, every maximal ideal in the coordinate ring is in this form, MP mod I, and we just showed that each one of those has to have dimension 1 as well. Right? That's kind of the idea here. So we do see now that here we have the dimension of m mod m squared is 1 for all maximal ideals m of the coordinate ring. And of course, that's exactly what we said before of what it means to be a Dedekind domain. Okay, any questions before we go any further here?
I have a question.
Sure.
So where did you use that the maximal ideal that we're dealing with here does contain the ideal where the curve vanishes?
The only part I'm using that is here at the very bottom line. When we're trying to say here, what is the dimension of m mod m squared for all maximal ideals of the coordinate ring? So everything up to this point, I only talked about MP, which is the maximal ideal of the polynomial ring. But I have to do this very last step here to realize that I really want to look at all maximal ideals of the coordinate ring, of OE. And this is where I use the lattice isomorphism theorem to realize that really all of those maximal ideals M are in the form MP mod IE.
I guess the substitution you did that depend on P being on the curve or no?
It did. Because yeah, you notice the MP here, it's x minus xp, y minus yp. So those are the coordinates, xp, yp. Those are the coordinates of the point P.
Okay, thank you.
Yeah, you're welcome. Okay, any other questions then? Okay, so now that we have some examples in place, let's try to write down some rigorous definitions, put everything in place. So this is kind of the unfortunate part of algebraic geometry, that you need a lot of definitions. You actually need a lot of commutative algebra in order to really state what you want. So I'm going to run through and try to explain some of the definitions that we're going to need. And again, remember that a lot of these will be worked out in more detail in the homework assignments. So let's just try to write out some definitions that we'll need coming from commutative algebra. Okay, remember, when O is an integral domain, then we define an abstract variety as spec of O. That was part of our definition of an abstract variety. So the philosophy now is, let's ask, how do the properties of our integral domain translate into properties of the abstract variety? Right, that's the whole idea. So we're going to try to take a look at different properties of integral domains and then eventually use those properties to write down fancier definitions for our variety. So the first thing I'm going to do is talk about the height of a prime ideal. So given an integral domain O and a prime ideal I, let's define the height as the length of the largest chain of prime ideals. So here, I'm going to write down a chain where I have I0, I1, I2, so on and so forth, all the way through I sub m that satisfy three properties. First, the one on the very left is the zero ideal. Remember, if I have an integral domain, then the zero ideal is a prime ideal. Next, the one at the very right is the prime ideal that we're starting with, right? So that should be kind of the end of the chain. And next, everything in between should be distinct, right? So I0 is different from I1, I1 is different from I2, so on and so forth, right? So each one of these better be different. So whatever the largest chain I have here, the largest integer m, is what I'm calling the height of a prime ideal. Right, so let me try to give you a few examples and a few properties of this concept of height. First example is the height is 0 if and only if we have the zero ideal. Right, so hopefully that makes sense from the definition here, because notice that if I have a chain that starts at the zero ideal and ends at our ideal I, then I don't move anywhere in the chain exactly when I is the zero ideal. Right, so again, the height is 0 if and only if we have the zero ideal. Next, let's go back to our polynomial ring in n variables. And remember that because we're working over an algebraically closed field, that every maximal ideal is in this form here. Right, so this x1 minus a1, x2 minus a2, so on and so forth. So in the homework, I'll have you to work out that the height of this maximal ideal is n. Right, so it does literally look like it's the number of generators that you have here. So the height of this maximal ideal is n. Right. So that's the first concept, the height of a prime ideal. Now you may wonder, how do I know that the height is a finite number? Couldn't it just be the m here is infinite? Well, that's the concept of the next idea, this idea of being Noetherian. So we'll say that a ring, a commutative ring, is Noetherian if every chain of ideals eventually terminates. So that means at some point, it's just not going to keep getting larger and larger and larger. At some point, all of the ideals afterwards are all equal to each other. Right? So again, this is the idea of Noetherian, that at some point, my chain of ideals, my ascending chain of ideals, has to terminate. Everything has to look like it stabilizes. And so I want to give you a couple of examples here. If you were to look at this polynomial ring modulo an ideal, so this is going to look very familiar to the way that we're going to define our varieties, then anything in this form is Noetherian. Right, so this, unfortunately, we won't have time to do here in this class, but this is a very standard exercise in any good commutative algebra class, that this quotient ring for any ideal I is a Noetherian ring. Next example, if you're given an integral domain that's Noetherian, then the height of prime ideals does exist. So that is that this number m, this integer m here, has to be finite. So again, part of the reason that we deal with Noetherian rings is that the height of an ideal is a finite number. Right? If you're not dealing with the Noetherian ring, the height here could be infinite, and then it's kind of pointless to play around with these things. Okay, so these are the first two concepts, the height of a prime and a ring being Noetherian. Okay, so any questions on these two concepts?
So the quotient being Noetherian, does that just follow from the polynomial ring being Noetherian and the lattice isomorphism theorem?
It basically does. That is right. Yeah, that is definitely right.
Okay.
Okay. All right, let's move on to the next couple of concepts. I want to define what's called the Accrual dimension. So yes, I know that this looks like it's spelled Kroll, but it's actually named after a German mathematician named Oliver Accrual. And this is called the Accrual dimension of an integral domain. It is the largest height as we range over all prime ideals. Right, so again, the Accrual dimension is the largest height as we range over all prime ideals. So one of the things you prove is that it's dimension 0 if and only if you have a field. Right, so this is actually one of the homework problems that I'll have you to work on this week. So dimension 0 if and only if we're dealing with the field. There are some equivalent statements if you want dimension 1, and we're going to come back and talk about this today. Our ring is dimension 1 if and only if every non-zero prime has height 1. And that's equivalent to saying every prime ideal is either the 0 ideal or a maximal ideal. Right, so again, dimension 1 is equivalent to saying that every prime ideal comes in two parts. Either it's the 0 ideal or it's a maximal ideal. Right? And then finally, the polynomial ring here, O, so a polynomial ring in n variables, has dimension n. And also, I do have you to prove this on the homework assignment this week. Right? So again, if you have a polynomial ring in n variables, then it has dimension n. So n should kind of be intuitively what you expect. Right? So n here does look like the number of variables. Okay. Next, we have the concept of integral closure that I'll try to walk through in the following way. Let's let K here be the quotient field of our integral domain O. So here what we're doing is we're taking a look at ratios of elements from O. So if you will, think of maybe O as like the integers, and then K here might be like the rational numbers. So literally just the ratio of two things coming from O. Right? Another way to define the quotient field is it is the smallest field containing our integral domain O. Right? You can write the definitions either way that you want. We're going to define the integral closure of O and K as the following set. So it's the set of elements from K that look like they are the root of some polynomial where the coefficients lie in the ring O. Okay, so this is kind of a weird definition, but again, it's going to look like the set of elements where they are the root of some polynomial where the elements here lie in the ring O. So it turns out that this O prime is also an integral domain, and it contains the ring O. So we'll give this definition. We'll say that O is integrally closed if O equals O prime. Right, so again, this is our definition. We'll say that our ring O is integrally closed if O equals O prime. So I do want to give an example later of a ring that is not integrally closed. Right, but for example, the integers will be one example of a ring that's integrally closed. So there actually is a criteria for double checking whether this always works. And it turns out that a ring O is integrally closed if and only if each of the localizations is integrally closed for every maximum ideal. So this is a fancy theorem from commutative algebra. We're not going to use this here in this class, but I'm only pointing this out to state that this looks very similar to something I stated earlier when we had our equivalence of how things match up with being a Dedekind domain. So I'm just going to put this here, but we're not going to discuss this at all here in this class. The main thing I want to discuss is this statement, that this polynomial ring over n variables is integrally closed. Right, so again, this polynomial ring over n variables is integrally closed. Right. Okay, so this is the concept of integral closure. So now, let's put everything together. Right, so all the different bits and pieces, and so I want to try to walk through the different definitions, what we're using, what we're not using, and why we want to use them. Okay, so let's go back to the very beginning. Remember that if we're given an integral domain O, spec of O is what we're calling an abstract variety. Right, that was our original definition. And the O here is what we're calling the coordinate ring of our variety X. Right, so again, I'm just writing down a very, very general statement here. So if you give me an integral domain, I can make these definitions. I have a variety, I have a coordinate ring. Now let's focus on the special case of an integral domain that is both Noetherian and integrally closed. Right, so the two of these together. Remember that Noetherian means that I can talk about the height of prime ideals, which means that the dimension is some finite number. Right, so again, that's why I care about Noetherian, that I can actually talk about the dimension of a ring. Right? So in this case, if we have an integral domain that's both Noetherian and integrally closed, then we call our variety a non-singular abstract variety. And in this case, the dimension is just given by the dimension of the coordinate ring. But you'll notice that also, I can write this here as the dimension of m mod m squared. Right, so the m mod m squareds here are going to be our cotangent space. So there is a way that I can make sense of tangents by looking at this weird set here, right, m mod m squared. So I'll come back and I'll try to give an example of this later, but this is just to say that to start with, again, abstract variety means that a spec of an integral domain. Non-singular abstract variety means that a spec of an integral domain that is both Noetherian and integrally closed. Noetherian is what allows us to compute its dimension, so some finite number, and integrally closed allows us to say something about the tangent spaces are very nice and well behaved. Right? So this is our first big theorem. This is what we mean by non-singular. So any questions up to this point here? Okay, all right, let's try to move on to the next concept. Here's an example. Let's look at this polynomial ring in n variables. Well, I mentioned before that this is Noetherian, I also mentioned that this is integrally closed. So now let's take a look at spec of this. I'm going to define an of f as this spec. Right, so now this looks really weird because remember that really what we meant was an looks like m spec, but now we're going to just purely abuse notation and call this spec. Right, so not just the maximal ideals, let's just say everything. So this is what we mean by affine n space. It's spec of this polynomial ring. And in fact, if you just stare at the definitions, the dimension here is n. Right, so remember I mentioned before what happens when we try to compute the Accrual dimension of a polynomial ring in n variables. It should be this dimension here. Okay, so now I formally have defined affine space for you as spec of our polynomial ring. Okay. All right, so let's try to even break it down to look at more specific examples from here. Well, let's say that we have an integral domain O where the dimension is 0. So we realized before that such an O has to be a field. So if you have a field, then that's clearly going to be Noetherian and integrally closed, because I mean, there's really nothing to check. And in this case, for our field, there's only one proper ideal, namely the 0 ideal. So spec in this case consists of one point. Okay, so again, if O here is a field, spec of O consists of one point, namely the 0 ideal. And actually, conversely, you can convince yourself that if you're given any abstract variety with dimension 0, then it has to come from a field. So what some people actually say, and this is a really crazy idea, you can actually replace all of theorems about fields, all of Galois theory, all by looking at abstract varieties of dimension 0. Right, so all of the theorems that you can think of for fields all correspond to abstract varieties of dimension 0. Okay. All right. What about dimension 1? So let's let O be an integral domain with dimension 1. Then in this case, we will call spec of O a curve. Right, so dimension 0, we can kind of ignore because that was the field. So now let's look at dimension 1. This is what we're defining as a curve, or if you will, an abstract curve. And in fact, if we have an integral domain that is both Noetherian and integrally closed, then we call such a ring a Dedekind domain. So here's your formal definition of a Dedekind domain. Right, an integral domain that is both Noetherian, integrally closed, and has dimension 1. That's what we're calling a Dedekind domain. And in this case, then we'll call spec of O a non-singular abstract curve. Right, so now we just translated everything back into just looking at the integral domains. Remember, we could have started the other way. We could have said, well, let's let X be the 0 set corresponding to some prime ideal I. We can let O here be the coordinate ring for that X. And then we know from the theorem before that this O, as long as X is a curve, O is a Dedekind domain. So now we're going in the opposite direction. Now we're saying, start with an O that's a Dedekind domain. Here's what we mean by a non-singular curve. Right, so just spec of O. So here's a weird example that throws off most people who work in the field. Spec of Z is a curve. Now, the reason why this is bizarre is there are no equations defining X. No polynomials at all. If you're wondering, well, what do the points of X look like? The points are literally the prime ideals of Z. Right, so the prime ideals of Z are my points. I know that Z here is a Dedekind domain. I know that it has dimension 1. I know what the points look like. Because Z is Noetherian and integrally closed, then spec of z has to be smooth. If you're wondering, well, what did the tangents look like? Remember that we had this thing here, the cotangent space, m mod m squared. Right, so this is one of the really bizarre ideas of algebraic geometry, that now you're completely generalizing everything by just looking at rings. Right, so if you give me a Dedekind domain, then I'll define for you now a non-singular curve. Okay. All right, any questions before we finish up with one last example? Okay, all right, let's take the last few minutes here and let's try to work out. Last example to piece everything together. So let's return back to our favorite elliptic curve. We'll work over an algebraically closed field F. And we know, based on what I mentioned earlier, that not only is OE here an integral domain, but it's actually a Noetherian integral domain. So for any A and B, we always have here a coordinate ring that is Noetherian integral domain, right? No matter what. Okay. So now let's try to figure out what's really happening in terms of all of the symbols that we had before. So remember that we have an embedding that says take an affine point P and relate that here to this maximal ideal. So again, here we're just taking an affine point and let's relate that to a maximal ideal. But now we have one more point on the elliptic curve, which is the point at infinity. So let's relate that with the zero ideal. Remember that the zero ideal is a prime ideal that is not maximal. So if we relate all of the affine points with M spec and relate the point at infinity with the zero ideal, then now we can identify all of E here with spec. Right, so that's why I can think of E here as just spec of the coordinate ring. Right, so I know where the affine points go, now I know where the zero ideal comes from. Okay. In fact, we actually see that the dimension here is equal to 1. Right, that takes a little bit of work to do, so I'm not going to worry about doing that today. But actually, we see the E here has to be a curve. Right, this is just using the definitions from before. So it's an abstract curve. Right, our elliptic curve here is an example of an abstract curve. But now, what about this idea of being integrally closed? Right, so we saw before that E is non-singular if and only if the discriminant here is non-zero. But according to our fancy theorems, that's true if and only if the coordinate ring here is integrally closed. So let me give you an example to show you what happens if the discriminant is 0, and therefore this coordinate ring is not integrally closed. So let's say that the discriminant here is 0. Then, as I mentioned before, this point here is the unique singular point on our curve. Right, so it's the one place where the derivative vanishes. Right, actually where even the Jacobian matrix has rank 0. So let me take a look at this element here, T. Well, T is not in the coordinate ring because I'm actually dividing by something. Remember, in a ring, I'm not really allowed to divide. So this here is not a polynomial in X and Y. It lies in the quotient field, but it's not in the ring. Right? It's like saying, take a look at the integers and look at 3/2. Right? Well, 3/2 is a rational number, but it doesn't lie in the ring. So this T here, it's an element, but it doesn't lie in the coordinate ring. Now, you can actually check, and this isn't hard at all, that T is a root of the following polynomial. So that is T squared minus this number is equal to 0, where this number here, you can actually check, is in the coordinate ring. So this means that t is the root of a degree 2 polynomial with coordinates no. So by definition, it's in the integral closure. So again, if the discriminant is equal to 0, I've found an element that is not in the coordinate ring, but it is in the integral closure. So this actually means that this ring, OE, is not integrally closed. Right, so this actually does show that if the discriminant is equal to 0, then our coordinate ring is not integrally closed, right, which is exactly what we expected. Okay, any questions on any of this? All right, well, let's maybe call it a day then. So please remember that the homework assignment is posted online. I'll have office hours at 11. And if you have any other questions, just feel free to let me know. All right, well, you all have a good rest of the day then.
Thanks, Professor Goins, you too.
Thank you, Professor Goins.
All right,
Thank
thanks.
you.
You have a good day.
Yeah.